So, my previous lecture, I mentioned, some of the basics of life, and so what we think how life starts. There's a branch of biology called exobiology, which is a study of life other than on Earth. Okay, now it's kind of boring and interesting depending on how you look at it. Very boring because we haven't found any life other than on Earth. So they have nothing to study. On the other hand, they are studying theoretically how does life work, and if we understand how life works, then maybe we can understand, what to look for. And so they do theoretical analysis as to how would life adapt in other environments, how would life originate possibly, and so forth. What conditions do you need for life, etc., etc. And so they do a lot of theoretical work trying to understand exactly what is life and how life works. All right, so that's the basic sort of thing here, exobiology. And obviously, what we want to know is exoplanets. What makes a planet actually habitable? Well, since we don't know any better, we assume it has to be in the habitable zone. We can argue exactly what makes a habitable zone, but this planet has to be suitable for life in some fashion. It has to be the right size. If it's too small or too big, it's also not going to have the proper conditions for life. It's got to be orbiting the right kind of star. If the star is too small or too big, it's not going to work. If the star is too close or too far in the center of the galaxy, conditions aren't going to be all that good either. And then the planet has to be the right composition. Gas giants aren't going to be very suitable. It has to be a rocky planet. Again, depending on when the planet formed in the history of the galaxy, it might have different compositions, different proportions of materials. That would also affect, what kind of things could be there, the kind of chemistry that could possibly be there. And there's a lot of interesting theoretical work that's going into this, showing that you have to have all the right chemistry going on in a planet. Otherwise, it's not going to be suitable for life, even if it's in the habitable zone. And so you got to have everything just right. Now, one of the problems is that, we want to figure out what's the atmosphere of a planet like. One thing we can't actually see the atmosphere itself, but if the planet passes in front of a star, then the atmosphere passes in front of the star, and it might show up in the spectrum of the star. Okay, so searching for life is one thing, but the next question is, what about intelligent life? Well, it'd be nice if we found intelligent life on Earth too. But what about intelligent life beyond Earth? Okay, we've never found life off of Earth. We've not found life anywhere in the solar system. We've not found evidence of life elsewhere. Okay, but if life is even possible out there, would it be intelligent life? Now, that's a big question. Okay, on Earth we have what we think is intelligent life. So they started thinking about intelligent life, search for intelligent life, a very long time ago, over 100 years ago. The idea was, if life is out there, how would we know it's there? One idea is optical signals. In fact, at the time, they were even considering the possibility there might actually be life on Mars. And so in Siberia, some people actually carved giant letters, giant trenches into the ground, and filled it with oil and set it on fire to make big flaming letters saying something to Martians in Russian. Or the possibility that there may be flashing signals at us. Optical signals are very unlikely. But with the invention of radio, people started thinking maybe they would send out radio signals. Because after all, radio signals will travel a very long ways. Radio telescopes are going to be a very common way of studying the universe, so maybe radio signals would be a fantastic way of studying the universe. And so maybe radio signals would be beamed out. In fact, Earth emits enormous numbers of radio waves off into space. All kind of radio signals are going out. You know, we got TV signals going out, radio, radio stations. We've got cell phones, satellite communications, all kind of leaking radio signals. And so we'd be a really bright radio signal. So if they were aliens were out looking at the solar system, they'd see all these stray radio signals that had a coherent pattern to them. And so maybe that'd be one way detecting something. Okay. So Frank Drake, engineer and astronomer at the who got his degree in engineering and astronomy, electrical engineering and astronomy, was one of our first radio astronomers. Worked at Green Bank Radio Observatory, and so when they built a brand new telescope there, he decided to test it by just pointing at different signals, different stars, and looking for signals. And on the third star he pointed at, he found signals, and they call this Project Ozma. And so after the Land of Oz from the Wizard of Oz, and so they thought, oh wow, we found something. Well, it turns out they actually were picking up signals from military flights that were flying in no-fly zones over the radio observatory, and they were broadcasting. And so so instead of finding extraterrestrial life, they just found military planes. And so, but this set the stage for questions. Well, how likely is it to find life? Okay. Yeah, and so and it's like when to find intelligent life, it is interesting that we don't really look for it here on Earth very much. All right, so what he did was he actually got to a lot of scientists together at a conference at Green Bank Observatory to discuss the possibility of life out there. And to organize his conference, he wrote an equation. This is how physicists do stuff. Okay. And so the equation has several terms. One, first, what we're trying to figure out is how many advanced civilizations are there out there. Okay. And it's equal to a variety of things. So the first thing in the term is R, the rate at which sun-like stars form. And we've pretty well determined about 1 per year. So the Drake equation is that it is equal to, the number is equal to the rate the stars form 1 per year, plus the fraction of those stars that have planets, plus the number of planets that are habitable around each of those stars, plus the fraction of habitable planets that have life, plus the fraction of planets with life that evolves into intelligence, plus the fraction of intelligent civilizations that develop technology that produces radio waves that we can detect, plus the lifetime of a civilization. Okay, so this is the Drake equation. And there's several ways of looking at this. You can say that R is 1. That's really the only thing we know. We can assume that all planets form stars, so 1 is the fraction of stars. Assume there's always at least one planet just the right spot to be habitable, because we do have one around our sun. Okay, so that'd be 1. Assume that if life can evolve, it always does evolve. So if it's habitable, it always has life, so the fraction's 1. Assume that if life evolves, it's always intelligent eventually, and so assume the fraction of intelligence is 1. And if it's intelligent, it will always develop radio technology and other advanced technological civilizations, so assume that's 1. And you can assume that such a civilization lasts for 1,000,000 years. So 1 times 1 times 1 times 1 times 1 times 1 times 1,000,000 is 1,000,000. And so you could say there's 1,000,000 civilizations that are out there. Carl Sagan did something like that, testifying before Congress in requesting money for the search for extraterrestrial intelligence. And so he came up with millions of things that are out there. Well, that's probably entirely wrong. The rate of solar star formation is about 1 per year. We got that. What fraction of stars have planets? Well, we think most stars actually have planets. So that might be close to 1. Binary stars may get rid of their planets, and we know a lot of stars are binary stars. So that's, so maybe we can assume that instead of 1, it's maybe half of stars end up with planets, keeping their planets. Okay. The number of habitable planets per star. Well, we said it has to be just right. If Earth weren't just right, it would not be habitable. So it's possible instead of 1 planet in every star, it might be 1 planet in every 10 stars is habitable. Okay, that's probably still being pretty generous, but let's assume that. So let's assume that that is 0.1. Okay, so the fraction of planets that develop life. So if they're habitable, will they develop life? That's a big if. We don't know. Life started fairly early on Earth, but there's indications that it got reset several times. Okay, so we don't really know. So there's a lot of things that can affect this, but we can assume maybe in about half of the planets that are habitable that they develop life. Okay, and so if they develop life, do they always develop intelligent life? Well, even on Earth, we've been here for a long time. Life got started a very long time ago, and only in comparatively recent years have we had intelligent life, and arguably. And so you can say, well, how often does this really happen? Okay, we're not sure. But again, let's be generous and say about half the time. Okay, and so then if you develop intelligent life, will it always develop radio technology? I don't know. Let's assume that about half the time it develops radio technology, if it has intelligent life. The next question is, how long does the civilization last? Now, this is not how long does the species last. It is how long the civilization lasts. Even on Earth, civilizations don't last all that long. But it's even more constrained than that. It's how long does the civilization use radio technology? Because it's entirely possible they could actually develop some other technology better than radio waves to carry signals, and then they might turn off all the radios, and then we wouldn't be able to detect them anymore. So maybe let's assume that they last for 500 years. So if we plug all those numbers in there, what we get is 3 civilizations spaced out over the entire galaxy. So there's either like a huge number of them and they're everywhere, or there's only a handful of them spaced really far apart. And so if that one's us and we can only see that much of the galaxy, then we have really no hope of actually finding anybody. And again, the distances involved are so huge, it's not likely anyone's visiting us. Okay. So this is the application of the Drake equation.